Hello dear friends, so welcome back to my channel. I'm Gerald Beya and I'm here to learn math together with you. So today we're going to learn about logarithmic function, how to differentiate logarithmic function. So let's take something to write. So here it is. So differentiating the natural logarithmic function. So that's what we're going to learn. What is a logarithmic function, natural logarithmic function? This is what we say log x, for example, and or lg. Sometimes I've seen it denoted as lg, and we know that from my previous video, we know that the function y is equal to ex, the exponential function, looks like this. This is y, this is the y-axis, and this is the x-axis. However, the logarithmic curve is different. It's if we draw a line of symmetry across the y is equal to x, so we will get something like this. So it is basically the reflection of the exponential function into the y by x line. So this is the ex and this is the log x. Okay, 2 points are very important. These 2 points are here. We know that anything to the power of 0 is 1. So here it's 0 or 1. And here it's going to be the inverse. So it's going to be 1, 0. 1, 0. So it means that log of 1 should be 0 then. Log of 1 should be 0. Okay, that's an introduction to logarithmic function. But just a moment, I see that there are some more things. So 71, that's the page. Let me quickly go to the introduction of logarithmic function. Maybe we can learn something more that I didn't say. And yes, here is a logarithmic exponential function. Yeah. Let's see. All right. The logarithmic function. Let's talk a little bit more about the logarithmic function so that we know, because differentiation is one thing, but the function itself is very interesting to know. What it is and how we use it. The graph shows the function y is equal to 2x. So we have like a graph, and this is like, it's not exponential, it's more like this. Let me correct this. So it's a rapid actually I have to redraw everything because y is equal to x to the power 2 to the power x is very sharp, very we say steady, I think. Okay, this is very 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 close to the x-axis, but it does not touch the x-axis, so it is asymptote. I don't know how I can represent it with my big fingers here. Okay, this is not doing me justice. Okay, but this is y is equal to 2x. Okay, not so important. Let's draw the line here of symmetry, which is, so this, we're going to have something like this that goes like really okay. So this is a reflection of it, and the graph shows the function y is equal to 2 to the power x in blue. That's here. I will just do like this. This is the blue, and the inverse of this function in green. So that's good that I chose green. Recall that the inverse function is a mirror image of the function in the y is equal to x. So this is our y is equal to x. Guys, that's very important, and since I'm also learning, so it means that if you have a function, the inverse of it, the inverse, so if we do an inverse, that's going to be like, if you have y is equal to, so we have to make it its inverse. So what we're going to have is root of y is equal to x, and then we just say substituting y into x, we'll get y is equal to root of x. So this is the inverse of this, and it means that for y is equal to 2x, so I will write here inverse, yeah, y is equal to x, so we'll have root the square of x, y is equal to 2. So we'll have, if we, I would say we say we inverse the the variable, so we get 2 is equal to, no, not 2, I have to put it in this form. No, that's not good actually. I don't know what I did. So here precisely we need to use some kind of log. You know, we have to say log y is equal to log 2x, for example. And then there are some rules that if this is to the base 2, I think this becomes 1, so the x come down. The x come down. You need to know how to transform these. And then, so, wow, y is equal to l. So if this is to the base x, so if you have like 2x, the x can also comes at the front. And we'll look at these rules. There are plenty of rules. So to get this inverse, we have to use log. When you have a power function, so you have to use log to get the inverse. So this inverse function is known as a logarithmic function. So as we saw, we will have x here and log y there, and then we just substitute places. We'll have y is equal to log x. So instead of this, we have this, y is equal to log x. Sorry, here. I don't know. It's a little bit messy, but I think you got the idea. You got the idea now. So that the inverse of y is equal to x squared is actually y is equal to root x. That's the inverse. And if we have what else? What is the inverse of y is equal to x? That's a good question. It's y is equal to x also. The inverse of y is equal to x is y is equal to x. Since the inverse of a function is a reflection of it in y is equal to x, so it will stay the same. It's not anything else. And if you have something like y is equal to x to the power of x, so we will have log here. You bring the x here at the front because you will put a log to the base of 2. this is equal to 1, so x times 1 is x, and log y. So if we substitute the places x and y, we'll have y is equal to log x. That's what I just showed. I've just shown, sorry, previously. So this is the inverse of this. Inverse. So it's a good revision to look at things in depth and understand what we're doing. So the logarithmic function is the inverse of the exponential function to the same base. That's what we just saw. And the green graph shows here is a logarithmic to base 2, because the blue graph shows 2. Yeah. So because we had 2, look at this. So if we want to eliminate this, we need a base 2 here. We need a base 2 here. And I think, you know, the LG is reserved for the base 10. So we should not use this here. We should use log 2. Why? Because the LG is reversed to the base 10, I guess. So that's something that comes back to my mind. So log to the base 10 is we denote it by this. So we already know that it's to the base 10. But if we're using a different base, so we should use like log, not LG. And so the green graph shows here is a logarithmic to the base 10 because the blue graph shows 2x. We saw that like 2x becomes x is equal to log x, the inverse. Sorry, here it's y then. Yeah. And the exponential has domain to set the the exponential function has domain the set of all real numbers with range the positive real numbers. So it follows to the same. So it follows that the logarithmic function is defined on a domain of the positive real numbers, and its range is a set of all real numbers. That was very difficult for me to read, as you've heard it. Let me just redo this. Let's say we have our y is equal to ex, not 2x here, and we have this, therefore y is equal to log x. It's for all the here is like the definition of the function. So it's for all real numbers. It means that the exponential function has domain the set of all real function. So the exponential. So real numbers of like from 0 to positive infinity to also negative infinity. So is greater than this and is less than this, if I'm not mistaken. Like, you can also write it like that. And I don't know, it looks like something like this to define this range. And so it follows that the logarithm is defined on a domain of the positive element, and its range is a set of all real numbers. So it also has solutions from here to here. I will use the green. So all these values here is negative and this is positive. So the so this will continue eventually to infinity. So this log function, this logarithmic function, goes to infinity, and it has also a range of like this, if I'm correctly writing this. Yes, so that was about the range and so on. So I'm sorry to lose your time a little bit with my mistakes, but I'm also revising. So if you will excuse me. Formally, we define the logarithmic function by, so y is equal to bx. This is the base, this is the power. And we say it can be then also like x is equal to log b y. So if we're looking for the inverse of this function, we just say log bx here. And so where x is an element of the real numbers, yeah, and y is an element of the real numbers, and y is greater than 0. Y is greater than 0. We know why y is greater than 0, because here it's asymptote. So y here, it does not cross x-axis. Y is never 0. It's greater than 0. So this is the definition of the function for this, and looking good. This is good. So I don't know why it says this. I don't know why it says this, like, the inverse of it or something. I cannot understand this size. Like, I think it's when you inverse it. And so these two special cases are worth remembering. So for any b log b, 1 is 0. So for any base, if you have 1 here, is 0. So, and also you have another important thing is, like, for any n, log b, therefore bn is equal to n. So that's what we use there, because we say if we have y is equal to ex, and then we want to find the inverse, we're going to actually we didn't have 2 here, we will have ln, I guess. This is another, this is the inverse of e, this is ln. That's what we're going to do now. We'll have this. So we're going to use ln y, then we're going to get ln y and ln x. Oh, one second. That's getting interesting. That's getting interesting. Remember this. We had this, and then we said if we do the log of it to the base 2, we'll get x times 1. Yeah, all these are equal to y, of course. So we'll get here log y is equal to x. We use this, and so this is a rule that for any n to the log b and a base here, so the n can move here times 1, because this is 1. So this is what it's saying here, and log of 1 is always 0. So that's why we have the graph here. When x is equal to 1 here, it's going to be 0. We just saw this previously. So this is done. We are getting better and better. But now remember, y is equal to ex. If we just define a log to the base e, which is 2 point, I don't know, 7 something, I don't know. I don't know the log number, the log value by heart, but you can check it on your computer, on your calculator. So here, if we do this, we're going to get 1 as well. So I think the log e is written just ln. The log is written just like ln, and that's how it is. Yeah, and and if we have this, we can say ln y, which is log e, and then we log to the base e, sorry, and then we have ln e x, so this is going to be 1. Ln of e is 1, is equal to 1. So that's why we get y is equal to ex. The inverse of it is ln y x, or we can substitute y and x, we get y is equal to ln x. So that's the inverse of this. So guys, we did a lot of inverse here, and we had the function definition, def, not very accurate, not very well explained, but we did it. And then what we did also the range of values. So that's also something that we look into. So what else is that we have some exercises here. So find the value of log this, log the base 2. What we do is just 2 to the power of 4. This is the same as 16, right? So 2 times 2, 4, 2 times 2, 4, 16, right? So we rewrite it like this. So you bet it, you guessed it, it's going to be 4, because this is 1 times 1 is equal to 4. Alright, we did the first one, let's do the second one. Log 2, no, it's not log 2, sorry. I have to do a lot of things, so I have to hurry up, and I also have to do my homework. I'm just revising here. So this should be to the base 3 then, so that we can solve it. So 203 divided by 3, we'll have 8 here, so 181. So this is 181 divided by 3. You will have 2 here, 7, 27. 27, we know it's 3 times 3 times 3. So 3 times 3 is 9, times 3 is 27. So we know that there is this plus 1 plus 1. So 3 to the power of 5 will gives you this. So log 3 to the power of 5 will give you 5 here, because this is 1 times 1 is equal to 1. Alright, next one, we have the log the base 10. We have 1000. Very easy, we just say 10 to the power of 3 and we get 3. That's the answer. And then we have 16 is equal to 2 to the power of 4, and it can be transformed into log 2. 16 is equal to 4. That's what we did. It's just the answers. I'm reading the answers here, so they are good. And now find the value of for example, we have log to the base 2 1 over 8. So find the value of it. So what can we do? We know certain things, like if we bring this up here, we'll get -1, right? And if we know that this is 8, right? Because 2 times 2 is 4, times 2 is 8, right? So because we put it up, so it's going to be minus, and it's going to be like that. So that's what we did. So we have this here, so we can rewrite it therefore as this. So we have 1 here, and we'll get 1 times -3 is equal to -3, and that's good. And let's do something else. We have log 8, 2. What do we do with this? We have 8, we know how can we do this? I think I have to do the inverse of something. If we have here, we have to be creative. We know this rule, right? But if we do like that of 8, so it's going to be written as this, right? Right? So why don't we just rewrite it like this, right? That's going to be 2, right? So we're going to get 1/3. And yeah, that's correct. So that's the answer. And now we have something more difficult. We have half to the base half, and we have 4. So we just have to think of something that will give us 4. What can we do with it for it to become 4? It's getting tougher, yeah. I think that if we root 4, we'll get 2. If we root 2, we'll get, what will we get? Anyway, we don't have to root it further, but we have to inverse it. So it's going to be to the power of -1. It's this, yes. So we have come to the conclusion that temporarily we can write 2 to the power -1, and we need 2 to the power -1 something to get 4. So if you have 2 to the power -1 is equal to 4, we just have 2 here, and we have 2 here. So this one is complicated. So we need something like x here. Okay, let me rewrite it. Log to the base half is 4. So we need this expressed in terms of half. So we know this is 2, and we know that this is, let's put it like this, 1. So how can we do this to become this? 2 divided by, no, times -half gives you -1, right? So something is telling me that if I do this and I do -half here, it will give me this. Okay, this should be easy. It should be easy. So for that reason, because actually this is 4 inside here, this is 4. 2 to the power of 2 is 4, so 4 multiplied by half is equal to 2 1/2, I think. Yeah. So this is a key here. That's what we are looking for. So we can write like log half, and and then we put half here. This is half. Actually, what I need to do, sorry, but it's not so easy for me, especially, I need to make half becomes 4. It's the inverse of it. I need. I know that it's this 2 2. So what I need to do is to multiply by something here. So what do I need here? I need x times minus half minus 1 is equal to 2. So x is equal to 2 divided by minus 1. So minus 2 then. Yeah. Oh yes, x is equal to minus 2. Oh gosh. So we should put minus 2 here, and then it's going to give us the answer is minus 2 because all this is 1. Yes, that's the answer. Okay guys, that was difficult, but we managed to do it. So if you have something like this, you like log of 4, what you need to do is just equate this. You say just half is equal to 4, and we put it on the same base, so we say like 2 minus 1 to 2, and then we say that you want this to be this. This is not equal, yes, we're just comparing. We should not write like this, we should just say like this. It's not the ratio neither, but we can, I don't know, just put it like this, just put a ball here if you want, and we want to do this. So we have to multiply by something to get this. So therefore minus x is equal to 2, and x is equal to minus 2, and we get the answer. I went through many things, but that was the conclusion of it. That's how you get this. Okay, let's do some more things. I'm being very slow here. We have this equation, and write this in the form of this. So if we have log to the base 2, 64 is equal to 6. We need to rewrite it in this thing. So what we want is to get rid of this. We want to get rid of the log actually. So we have to put it in power. We need to the base 2. So x something is equal to 64. So x to the power of something, y is equal to 64. So what we need to do is so I have to say 2. I didn't write it in a nice way. I should be able to be more sharp on these things. Is equal to 64, right? So 2 to the power that is equal to 2 y. I don't know what it is. So well, it's just it's the root of x, yeah, 64 to the root of x, root square of x. So I don't know, we just have to divide by 2, yeah. So it's going to be 3 here, 1, no, 2, sorry. So this is 1. 32 divided by 2 is 1, 6, so this is 2, and 16 we know it's to the power 4, right? Because it's 4, 4, 4 times 6. So 4 plus 2, it's 2 is equal to the power of 6. So we got the answer. I am not really good at these, but we managed to get the answer I will revise it therefore. Just one moment. We're still revising logarithmic as we should do, while we should be doing logarithmic differentiation. But guys, just bear with me. So log, we have log 264 is equal to 6. What we saw is that we can rewrite this as 2 or 6, and this will be 1. 1 times 6 is equal to 6. But that's proof, that's proved, but that's not what we want actually. We want this in the form of this. I understand. What we need actually, this value is y, and this is what we have to figure out. But to the base of this. So we saw that this is 2, 6 is equal to 6. So this is 66. Yeah. We can do something else actually. No. We need this. So this is y. Oops. This is not y. This is well, it's just that here the answer is like this. I just look at the answer. The answer is just this. So we just transform this here. But of course, I don't know. I think they should not have even given this here because it's confusing. Just transform this in this form. Ah, okay. I understand. That was much simpler. Now I understand. If you have like log 264 and you see that it's equal to 6, of course it's going to be 1 here. This is going to be 1, and what is here is going to be this because it's 1 times 6. So we went through all this and the answer was right in front of us. Right in front of us. So, but I understood it at the very last moment. So here, what we need is just like log k p is equal to m then. So I mean, yeah, this p of course, but kp is equal to m. So I think you got it by now, because when we will have kkk here, we will have p here. So that's it. So we can write m is equal to kp, therefore. Easy. Good. And now we have done this. There is also another exercises. We have x is equal to log by. So we can rewrite this easily. We can say log bb x, yeah, is equal to x. So what do we need to find here? Write these in the form of x is equal to log. Now we have to do the inverse. We're learning how to transform something from one form to another, from the power form to the logarithmic form, and so on, the log form. Now we have to learn how to do the other way. Okay, let's do that. So we have this given to us. This is equal to 0.008. So we can rewrite this, I think. What if we will write like 8 times 10 to the power of minus 3, I think. Yeah. And yeah. Mm-hmm. So what is it about? Here we have like 2 to the power of 3 times 10 to the power of minus 3. We need to have something like that. Hmm. What we need to know is like if we do log 5 here, 5, we will get minus 3. So here, but this is not b. If this is b, this is y. Why is this? Why is this? So always we have to remember there is x is this, but y is equal to base x. So I'm not good at these things, but I'm learning that if you want in the power form it's like this, if you want in the logarithmic form it's like this. So from this conclusion we should be able to work our way out of this. So let's do the job now. So we have this is 3. So this is that. So y is equal to 0.008. From here we can tell this. Y. So we need to put a log to the base of something to this, and it's equal to x. X here is minus 3. So we need the base here, and the base is here. The base is 5. So it's log 5. If you compute it, you can certainly find it. Yeah, that's the answer. We need to know both forms, how to write them, you know. Yeah. Then you will understand how to transform one quickly into the other, how to rewrite this quickly in this, and vice versa. All right. So let's have another example. We have h5 is equal to r. So we need to rewrite this. So we know that this is y. If we want to, sorry, y is equal to b to the power of x. Yeah, that's what I need to write here. And x is equal to log b to the power of log by. So here I have this x, this b. So log b, log b, and this is y. So I will, this is y. This is y. So I have to put r here, and then x is x here. We have 5. So log hr is equal to 5. That's the answer for this. Let me check. Yeah. Alright, so summary, quickly summary. If we have log k m is equal to p, so if we have to write it in the form of so is equal to y is equal to how do you call this, bx, yes, y is equal to bx. We need to write this in this way. So we just know that this is a power, this is x, this is x, and this is k. So k p is equal to m. Yeah. Another way is just like kp, m is equal to kp. We get this from this because we want it at the same. Alright, and the other way, if you get something like log km, no, not this one, h to the power of 5r, we want to write it in the log way. So we have to say log, this is y, so here, and is equal to 5. So this is going to be h. Yes. Not so easy, yeah? Not so easy. But some people just say like log h 5 is equal to r, and this is equal to 5. But you have to log on the other side as well. Guys, I think I start to understand. Like instead of like, losing time, you can get things done by just using real mathematics. So if you have h5 is equal to r, we log here to the base of h, let's say, and we log here to the base of h. So this is going to be 5, and we are done with log hr. That's the answer. What was so complicated? I don't know, but there was also like log km is equal to p. So here we have to transform this. How do we do this? We know that we just put this k here, and m. No, it's not. It's going to be p. Yeah. So we know that m is equal to kp because this is the unknown. This is 1, so we want p here at the end. So kp is going to be, yeah. Now it's easier, especially when you have to transform a log into exponential. Okay guys, so let's move forward. I have to look at the time. Yeah, we're almost 1 hour into this. I think this lesson is going to be in 1.5 or maybe 2 hours. I'm sorry, but I need to prepare myself for what's going on at the university. But we have this on the same axis. Sketch the graphs. This and this is this. I have y is equal to that, and y is equal to 1.2x, and I have y is equal to 1.5x. So I have these, and I need to sketch them all on a graph. So what do I do? Well, I can say, for example, here, this is y, this is equal to x. Anything to the power of 0 is 1. So we know this. We know. Yeah. So everything will cross to this point. Everything. Now we have what else? We know that y cannot be 0. It will approach a 0, but it will not be 0. But 2 will increase and 1 will so what happened? 0.12. Let's try this times 2. This is going to be 14, 0. So this one is getting smaller, right? When x increase, y is becoming less. So it's going to be like this, and y is equal to 0.5x, right? Now let's look at the other one now. So we take y is equal to 1.2x. We know it's going to go through this, but we want to know how it behaves. Let's say 1.2 times 1.2, this is 1444, if I'm not mistaken. So from 1.2 to 1.44, that's because x is 2. When x is 1, this and this. So it's actually increasing. So y is going to increase together with x. In that case, I'm going to write it like this: y is equal to 1.2x. And let's look at the last thing. We have y is equal to 1.5x, and we want to know how it will behave. So when x is 1, we have 1.5. When x is 2, we have, so 15 times 15, we have 155. This is 5, 6, 7. It's 7. 150 plus 75. It's 5 to 225. We have 2 points here. So from this to this, we see that it's increasing. So when x increases, y increases as well. So when x increases, y increases as well. So it's going to be something, actually it's not below this, because it increases faster. It's going to be here, something like that, not this one. So here, just to make things more beautiful. And I can use yellow. Yeah, nice. So this is going to be our last y is equal to 1.5x. So this is exactly how they plotted things, and it says that this one is going to be here because the base is bigger, so it will increase faster, so it should be above it. So in part A, the base value 0.7 is less than 1, so the function decreases as x gets larger. In part B and C, the base values are larger than 1, so 1.2, 1.5, and so these functions increases as x get larger. Note that C is steeper than B because C has a greater base value. That's exactly what we did. I didn't read anything, but we try to do things and it worked. So now we have come to another level. We have log. The yellow is not bad as well. Yellow on black. It goes very well. And so this is some properties. So when you have something like this, you can rewrite it as is equal to log x plus log y. It's plus. Yeah. So if you have anything is equal to like that, 7 for example, you can say, okay, I decide to put a log here, yeah, and I decide to put a log here, and I decide that it's going to be to the log to the base 7, right? So I'm going to have 1 here, and then I'm going to work on this. I will get log, of course, 7x plus log 7y, and you can do steps, you know. So this is how we do it now. We're getting better at this, I think, slowly. And we have also like x divided by y, and it's going to be minus log y. So when we have product, it's like this. When we have division, it's like this. And we have another law, which is log properties, sorry, n, and we can always send the n at the beginning. Yes, and it says these results are true for logarithm of any base, so always true. It's always true, always true. All right, so always true. And so let's do some exercises quickly if we want to practice express this as a single logarithmic or number. So logarithm, sorry, express this as a single logarithm or number. So we have log to the base 5, 4 plus log to the base 5, 7. So since they are of the same, we know that it's 4 times 7, so we're going to have log 5, 28 here. So that's the answer, I think. And we cannot simplify this to the base of 5 because 28 cannot become to the base of 5. Okay, that was the first one. And let's do the second one. We have log 64 plus log is it plus? Yeah, it is 9. we know that they are the same base, we can multiply them. Therefore, it's going to be, let me charge this, and so many things to do, and these guys. Alright, so we have this, and it's going to be 36 here. But here we see that we have 36 and 6 to the power of 2 is 36. So we know that y is here, b is here, and x is here, so you know that it's going to be 2, the answer. So we are quite good with these now because we've revised, but let's see if there are some other things here. Exercise 9. So let's do this. We have a here, we have log xy. What do we need to do? Express this in terms of log x, log y, and log z. Okay, here we know that is this. So there's nothing complicated. And b, just reminding the properties, I guess, just for you to remind yourself of the properties. So what do we have here? This is z, right? It's not 2. So what do we need to know? This is complicated. First of all, we need to know that it's complicated. And yes, this is 2, but this is z. What do we need to do here? What do we need to do here? Let's say that xy is equal to p. So we'll have log p2. No, we cannot say log p2. We have to put this here. I don't know how to solve this, but I will try to do it. So I have this, I will erase this. So what is going on here? So we have this. So this is easy. We know that log p minus log 2. Yes, this is good. Now we can solve this. We can solve this because we know that p is equal to something. P is equal to that was x times y to the power of 2. So we know we have this result, that's z minus log z, right? And let's do this part now. We have log xy 2. So we know how to do this. We just say plus log y to the power of 2. This is log, 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 this is y, this is y. So in the end we will have something like log x plus log y to the power of 2 minus log z. That's the result. But I prefer to do this because the answer is correct, but it's just that I don't know if these two things and divided by this log, if you can just put it like that. So I did it step by step, not to get messy, so I use a substitution and it's correct. And we have something even more complicated, at least it looks more complicated. We have x3, y2, 4, no, that's z to the power of 4. Okay, everything is square root. So how do we proceed here? We have we have log, we have such a big thing, we have z to the power 4, we have half here. We know that we can do like this for anything, for any log base, we can do this. So we just did it. The other thing that we know, let me erase this. The other thing that we know is that now we can safely just say half log x3 plus log y2 minus log z4. And I think that's the answer. Let me check. They say that you can rewrite this. You can put like the 3 2 here, log x plus 2 log y minus 4 log z, and this should be like 2 divided by 2 divided by 2, so this is 1, this is 2. So you can end up with something simpler. That's true, I didn't see this, but the answer is helping me to understand. Plus log y minus 2 log z. So that's the correct simplified answer, and this is just something in between, but it's still good. But just remember that this is for all of them, so if you multiply all the terms. Good. I'm quite satisfied with this revision, and here it's given that log to the base a3 is equal to x, log to the base a is 5 is equal to y, and log a to the base 10 to not the base 10, sorry, log a, they are all to the base a, but 3, 5 and 10 is equal to z. And then we have to work with this. We have log a is equal to 50, no, log a 50, sorry. So what do we have to do is express this in terms of what is given above. So it's just basically playing with numbers, because we know that 50 times 5, 50 is equal to 10 times 5, right? So we know there is 5, there is 10. We can just say log a is equal to 5. So 5 is going to be yz then. So this is the answer. Yes, it's the answer. And there is more to it. There is more to it, because this can be expressed as log a5 plus log az, sorry, y z, and we have this here, we have this here, Yeah, I think this is the final answer. This is the final answer. Just that this is 5, yeah, and this is 10. We rewrote this is here, and then we found this from there, and we rewrote everything here. Yeah, okay. I'm just a little bit confused by the answer that they give. They give just the y plus z, I don't know why. So, well, maybe it's just enough. So now we have log a 75. So what we're going to do is, how can you get this? Um, if we divide it by 5, we'll get 15, right? And how to get 15? 3 times 5 again. Yeah. Yeah. So it looks like it's y times y, uh, y times y, and then what? Times x. So you have basically log a y plus log a y plus log x. So that's true. Let me rewrite it in a more presentable way. So I'm just tired, sorry guys. 75, we know that 75 is times divide by 5, we divide by 5, we'll get 15, we divide by 5, we get 3. So we have 5, 5 and 3. So it's log a 3, which is log a 3. Yeah, I understand from the other one as well why it's just plus, it was just this. I understand now, because yeah, I understand. Okay, now we have this is a actually, plus log 5 plus log a5. Now you get this 2 log a5, right? Log a5, it's x, but this, we can send this here. We'll have 2 log a5 to the power of 2. This goes away, of course, because we send it there with x plus, and this is y to the power of 2. The final answer, I'll write it here, is x plus y to the power of 2. Yes, that's good. No, no, no. Sorry, we don't do this. We just keep this here. Because if we do this, we will have, we will not have, this is y. So it's just 2y. It's not to the power. We already, yeah, that was wrong. Okay, that's done. And I'm tired now. Sorry guys. Let's do it. Just one last here. Is equal to x log a5 is equal to y, and log a10 is equal to z. So these are the givens. Now we have log a 0.75. A little bit more complicated. So 0.0.75 is just 75 times 10 to the power of minus 2, right? 75, we know that it's 15 times 5, So to get 75, we know that we have to 5 times 5 times 3. That's 75, right? And let me erase this. And what else? To get 10 to the power of 2, we have log a 10 here. We have 10 to the power minus 2, we need minus 2 here. So it's basically minus 2z, because this is z. So basically here we have how many 5? We have y 2 times, so we have 2y plus x minus 2z. Let me see. Yeah, the answer is right. 2y plus x minus 2z. We got it. Okay, I think you also got this. So but just for you to know, like, I will write the answer here. If you're following this to learn together with me, is just that the correct form was to represent it like that, yeah, and that from here you can see is like x 2y minus 2z, because it's like divided. That's the most important thing, divided. This is divided 10 times 10. This is a better way to represent it, of course. Okay, so then we have exercises, and we are done with the exercises. And so we are done with logarithmic function. We know quite well now how it works and so on. And let's say that it's just the first part of this video. So I'm going to end this video because I don't want someone to watch a video for 2 hours. So it's just logarithmic function. It's just going to be about logarithmic function. I'm going to end this, and I'm going to start a video with the differentiation of the logarithmic function. Okay, see you in a bit. Thank you. Bye.